Are you sure that wasn't an exam you had us take it there this morning?
No, that was a quiz. Why would you think of it as an exam? Hello, who was that I was speaking to?
This was Tim.
Tim, you think that was an exam or a quiz?
I guess what I was trying to say was it was harder than I expected, but I studied well, so whatever.
Oh, what did you expect? That was an easy one. You haven't seen a hard one yet.
See, Pavel agrees with me.
Oh yeah, but Pavel, he'll agree with anybody. No, that was a quiz. I gave very similar quizzes when we were face to face. Unit 1 was a 1 hour quiz, and Unit 2 was an hour quiz. Um, no, last time I think it was Unit 2 and Unit 3. It was cement and aggregates. Sometimes I give, depending on how we're studying what unit at what time. But anyways, typically I would give 1 hour quizzes, and that would be basically 50 minutes because when you have 10 minutes between classes, and most students complete it. So I gave you 2 hours. Unit 2, the aggregates, was quite a bit reduced than you typically give for a 1 hour quiz. So I noticed some finished within an hour and 3/4, an hour and a half, which was about on par for both of them. So how many found it really tough? How many found it good?
It wasn't tough, but the format that your quiz was in, it was similar to Natalie's midterm last year.
In what way, like, as far as format?
Just what the whole test looked like, the length and the question types and everything. It's hard to believe that it was a quiz.
Well, the thing is, hold on, I'm going to reduce my speaker volume because I got my headset on, the cracked up a little higher. Many times I don't break them up. You say section 1, true and false, section 2, multiple choice. I integrate everything together. I throw in some calculations with some short answers. You might get a couple of true and false, and then you may have a couple of multiple choice, and then another short answer. But I thought this way, you'll know, okay, I'm going to do all my true and false first, get them out of the way, or I'm going to do them last, do my long answers first. So I just kind of summarize them under 4 sections, just to kind of make it easier. What type of quizzes are you normally expecting? I don't give 100% true and false because I don't think a true and false is a proper way of assessing anybody's knowledge on anything.
I mean, I don't think it was a problem of like the format. It just the length was kind of misleading because you said quiz, and usually a quiz is like, I don't know, 10, 15 questions. But it was 9 pages. And when we had Geotech 1, the exact same format was considered a midterm. So I don't know.
No, you have a midterm. Yeah.
I know we have the midterm, but Geotech 1, Natalie used the exact same format with true and false, fill in the blank, short and long answer. It's just like when you're expecting a quiz, you go in and you're like, oh, it'll be 10 questions, and then we're hit with.
Well, why would I give you 2 hours? Why would I give you 10 questions in 2 hours? When I sent you the email mentioning that it's a 2 hour quiz, and even on the block schedule says 2 hours, obviously it's going to be more than 10 questions. Mind you, I've given quizzes a half hour. I've given quizzes 45 minutes, that type of thing. So.
No, I guess our question is like, is the midterm going to be similar length and style, or is that going to be way longer than this one?
No, it'll be 3 hours, but you may not have any more pages.
Right.
You got to remember that I spread it out sometimes because some people write small, some people write big, some need more. I mean, those that don't have printers and are writing their answer on loose leaf paper and then they're going to scan it, okay, that's different. I could give them a 2-page, one question after the other. Okay, you see what I'm getting at? But because I'm allowing room to write on it, typically these quizzes or exams are written in the gym or in the classroom, and you get the exam printed for you or the quiz is printed for you, and you write right on it. So we're going to spread it out, like I said, because some people need more room than others. So that if you brought everything up, you'd find out it wouldn't be 9 pages. But anyways, the length I think was good. Most people had no problem finishing it. If you had trouble getting it into the Dropbox, it took too long. Typically, I give 2 hours, and out of that 2 hours, you allow 15 minutes for yourself to put it into the Dropbox. I've had other classes that complain about it, saying, well, you're taking away from my writing time. No, your quiz is actually, or your exam, or your test, whatever you want to call it, is actually 1 3/4 hours long. The last 15 minutes you should allow for Dropbox. And if everybody waits till the last minute, and 5 of you are trying to download it at 1 minute to the cutoff time, someone's going to get bounced out. So that's why I also made it 11 to 11:15 as Dropbox. Obviously, the Dropbox was open right from 9. In case it only took you an hour to write the quiz, you could download it, submit it at any time. So someone took 1 hour and 57 minutes to finish, so maybe. No, it's not that you're dumb. Don't ever consider yourselves dumb, guys. Everybody can learn something, and everybody can learn just about anything. It's going to take some people longer to grasp some things than others, and vice versa. So don't ever think that you can't do it. Okay. What bothers me is when people do not put their name on every sheet of paper because they just jump right into the exam and they're trying to make use of every 2 seconds. If you can't allow 2 seconds to write your name on every page, then don't even bother writing it. You don't know your stuff. I'm serious. If you need 2 seconds to write your name and you need that 2 seconds to write the quiz, you don't know your content. So just hand in a blank exam if that's the case. Okay, it takes 2 seconds to write a name on it. And you may realize I'm anal about that for the simple reason when I mark in paper copies, many times I take them apart so I don't have to keep flipping. And if I take the staples out or I take the exams apart and they get mixed up, which they can, especially when I'm scanning or I'm printing something on a printer, I lose them. I don't know whose writing is whose. That's why you have on every sheet, you'll see a place for it say student name, and that's for you guys. Put your name in it. I've had exams and quizzes submitted with no name anywhere. I'm justified to just say no name, no mark. Now, I don't want to be that cruel, but put yourself in the instructor's shoes. You think it's not a big deal, but when you got 10 pages times 36 exams or quizzes or tests, and you have to fix each page up for a student, and there's nothing worse than having something submitted, 1 page in landscape, 1 in portrait, 1 in landscape, 1 in portrait. You try and mark a PDF copy and try and make time for it. You're flipping back and forth, rotate halfway, rotate counterclockwise, rotate clockwise. Okay, so put yourself in the instructor's shoes. Marking isn't easy when you got to fix somebody's pages. Or they download page 1, page 8, page 3, page 5, page 6. Again, it takes 2 seconds to put them in order. If you need those 2 seconds to write your exam, you don't know your content, period. Aren't I ornery this afternoon, eh, guys? Okay. Any questions other than that? Another thing I've noticed, guys, these are our closed book tests, quizzes, whatever. Once you download at 9 o'clock, you download your quiz. There is no other reason why you should have to go into learn again. I can track, I can see if you go back in 3/4 of an hour later, 10 minutes later. There's no reason for it. If you look at the Dropbox before the quiz starts, in plenty of time, you'll see when it closes. I usually send an email giving you a little bit of heads up about the quiz and what to expect. And in that email, I give you times of start, times of completion, opening of Dropbox, closing of Dropbox. So typically, when I see someone going in an hour later into Learn, somebody's searching. Or for some reason, I see them go into the lecture notes, or I see them go into the lab procedures, or I see them go into an assignment. What am I supposed to think, guys? Keep that in mind. I can track, I can see who opens up when at what time. I even know your IP addresses from where you're writing.
I feel exposed.
You feel exposed. You can run, but you can't hide. Is that it? Okay. Something like that. Okay. Any questions? General. I'm just reading some of the chats here. Time was fair. Yeah, right. From Pavel.
Can you hear me at all?
Oh yeah, I can hear you.
Yeah, okay. Do you mind if I just chime in really quick with
No.
my 2 cents on the quiz?
Yeah, go ahead.
I thought the majority of it was definitely fair. And I can see where you're coming from when you say, you know, for us to put ourselves in your shoes with the names on top of the paper. Like I get you've got your little things that, you know, are cute. I think from a student's perspective, what really caught me off guard was the problem solving portion of it and the amount of mathematics that were involved with it. When like in our classes, we went over no examples of mathematical problems. So that's what took me most of my time and really threw me off. I don't know if anybody else feels the same way, but I just think going forward, if there's gonna be, you know, that kind of content on it, I would have appreciated if we had gone over some examples from like start to finish in class.
Okay, Michelle, first of all, that means you didn't do the lab. Those were lab questions.
No, I definitely did the lab, but just the even like, so again, like you saying us to put ourselves in the instructor's position.
Yeah.
I'm asking you to put yourself in the student's position here, where we're doing this remotely online. Okay, it would be completely different if we were in class and we were in the lab and you're there all the time and we're able to pop by and like ask questions and get like straight up feedback from you. This is all completely different. Even if you do the lab and then you sit there with a test, that the way this test was, this test, it seemed like was like intended as if we were in class learning all the time with you every single day, able to pick your brain. Just to me, it was kind of on a different level, and I was caught off guard by it. Is all I'm.
Michelle, how many times, Michelle, did you contact me in the last 2 weeks online by email for help?
I didn't think well, honestly, John, our mark from our lab wasn't very good, so I probably should have, but like we got the lab done and I understood the lab completely, but it's just, again, like the test, and I don't think I'm the only one who feels this way, and I'm not trying to like come at you. I just think it would be like, if rather than just like going over PowerPoint slides in class, if there's going to be mathematical problems, I don't think doing 1 or 2 like in front of everybody so we can follow step by step and we know exactly what we're doing would be a horrible idea.
How did you find the assignment on mass volume density relationships that I was uploaded for you? How did you do on that compared to my answer sheet? Did you get them right or?
No, but again, you look at the answers and then you kind of understand it. But I was just, you know, I guess.
First of all, Michelle, let me ask you, did you do the assignment, mass volume? You did.
Yes. Yeah.
And you did quite well?
I did okay. I usually do all right, but it's also a whole lot easier whenever you do get stuck and there's no time limit.
Yeah.
The panic situation, you know what I mean?
Oh yeah, I hear you. No, you've got a valid point, and I don't gripe you for speaking up. In fact, I'm glad you did, because this is one thing you guys are going to have to learn, and that's even from our perspective. It's unfortunate, but with this COVID and online, there's more onus on the student to work on their own, because some students obviously cannot sit in on the lecture because they're working or whatever, or they're babysitting, so they're going to work on it in the evening, and that's fine. That's one of the beauties of online learning, is you do it at your own convenience. That's why we do the recordings. Yes, it's not as ideal as working in a classroom, and I prefer in the classroom because there's better dialogue. You open up, even throughout a lecture, whether you're using a PowerPoint or whatever, that's just as a background. But you get dialogue going, you get discussions going in the class, whether it's a lab or whether it's a lecture. So I hear you 100% that it's unfortunately, with this, the onus is on you students to do more on your own. Unfortunately, there were times maybe through high school or even first year where you may have been somewhat spoon fed. Sorry, guys, that's changing and it's unfortunate, but we've got no other means with this COVID-19. So the onus is more online learning. I've taken some CAE courses online and I hate it. I absolutely hate it. My daughter used to say, Dad, suck it up and go work. I prefer face to face. Hey, I hear you. But what I'm trying to stress too is I will help you all I can, but you have to ask. If I don't hear from you, I'm assuming, and maybe I shouldn't assume, that there's no concern. Like I say, it may be not as convenient as putting your hand up in class and say you have a concern, you have a problem with something. Yes. But reach out to me. I've had students do that. I've had students on Sundays and Saturday evenings at 10, 11 o'clock if I'm at my computer and I answer them. Okay. So the formula sheet too was pretty straightforward. If you looked at the definitions in the formula sheet, I think it would have been fairly straightforward. Here, let me just read some of these chat lines, some of these questions here. If you understand the concepts of density and specific gravity, it shouldn't have been that difficult. That's true. Jim, men are talking. Hey, guy, come on, guys. Last calc was tough. I think Mitch and Mitch are just asking for you to put yourself in our shoes. Like you are asking us to, yeah, oh yeah. No, I know where you're coming from, but what I'm trying to do is also mention to you that it's not as difficult as it seemed. When we're used to something one way, it's hard to grasp something another way. And that's understandable. That's human nature. And again, what I have to really mention is the onus is more on the student now. You know, we have a condensed format. We've taken a 24-week program and we're cutting it into 12 weeks. And that's tough. So that means 6 weeks for concrete and 6 weeks for asphalt. And there's a lot of content there. There's a lot of content there. So don't get alarmed when you see a problem. Sometimes it seems worse than what it is. If you look at it and take it step by step. And formula sheets, I mean, you're lucky. Formulas sheets I've always given out, but you know Natalie doesn't agree giving you guys formula sheets. I mean, you probably had her in mass weight volume relationship. Did she do those with you guys last year? Yeah, she did that last year with you, right? For soils? Someone speak up, right? You guys do mass weight volume relationships on fine grained soils with Natalie, right? Yes. Does she give you formula sheets? No. I allow formula sheets. I mean, I'm not a firm believer of always using formula sheets for the simple reason the students get too dependent on them and they spend way too much time looking for a formula instead of understanding the concepts. So I like Natalie's idea. If you know the 5 or 6 basic formulas for mass weight volume relationship, there's not too many problems you can't solve. No formulas, but multiple examples covered in class, including difficult ones. Yes, and I do that with my structural group. We do a lot of mass weight volume relationships. I've got about 3 sets of problems with about 15 to 20 problems in each set that we go through. We don't do them all, but we go through them. But again, how many of you asked for additional help on mass weight volume or specific gravity calculations? Anybody? Did I miss the email or did I miss the contact? I realize it is not the same as being in class, but how many of you reached out to me?
I mean, to be fair,
Yeah.
like doing the labs and the assignments that you gave, it's a little easier because you're obviously just introducing the concept, and the quiz is meant to test our idea.
Yeah.
But the test was taking it to the next step, and I don't think we were adequately shown how to do that next step, and that's where kind of a lot of people found troubles, I guess.
Okay. Well,
So like, I don't think there was a need to email you. Like, I'm personally speaking, like I found the last question a little harder. I did it. I finished in time, whatever. But yeah, I found it a little more challenging than the assignments and the quizzes or the labs that you gave. And
What was it that stumped you on the last question? Net
uh,
volume,
just
total
yeah,
volume, net
finding the
volume?
volume. Yeah.
But the formulas are given to you. Total volume is net
Yeah,
volume
but
plus
the
absorption.
wording is different than the ones that were on the lab, so that threw me for a loop as well. And then like,
Okay, right. I can understand that. But
yeah,
start to think outside of the box. You're not always going to read things the same way. It's impossible.
no, yeah, I
When
understand
you're
that. But
voicing,
like, when you're learning something, if you're taught one way and then shown a different way, right, you got to adjust. And doing that adjustment during the test is a little difficult. And like
well,
personally, I needed
this
to
is
go to the bathroom during the test, and I couldn't. So like, I was dealing with that problem too. So you
why
know,
couldn't you go? You were at home.
oh, yeah, but like, I needed all that the time I could get. I was putting my name on the sheet and like was running out
Oh,
of
come
time. You know.
on.
Oh,
How long does it take you to write your name?
well, I could have like gone to the bathroom in that time. You know.
Well, you could have. Take your sheet with you.
Oh my God. Yeah, I
I've
guess
seen,
so.
I've seen a guy in the men's washroom standing at the urinal, pardon the language, and texting. Like, come on now, that's being a little bit.
Wow, yeah.
Yeah, that's going too far. This was at
That,
Red River last year. I
that's
did a
skillful.
I did a double take, and I look, and he's texting at the same time. But anyways, neither here nor there. So let's don't worry. I was working in the washroom. Okay, I hear you guys. Valid concerns, valid points, but try to think outside the box. Okay, you have to. And one thing I always tell my students, I'm here to help you, but I won't babysit. I do not babysit. I did that. I'm finished. My kids are in their 30s. I don't have to babysit anymore. I will help. I'll do everything I can to help you guys. But those that help themselves, I'll help them. So you have to ask. Don't be scared to ask because I see it in the classroom. I ask a question, and you probably know it because you've been in the classrooms. Maybe one or two are individuals are the only ones that ever answer a question. Maybe a little bit more, maybe three. I don't know what it is. Whether students now are afraid to ask a question or to answer a question. Shouldn't be. Shouldn't be. We're all in the same boat. We're here to learn. Okay. I always say I could have been a doctor if I wanted to, but I didn't have the patience. Ha. Anyhow, old joke. Okay. I'll hear you. I'll keep that in mind on the next quiz. And hey, when there's assignments, if you need extra help, by all means, let me know. Let me know. But you have to speak up. Okay. I've got some 80 students, or I had some 80 students in total. So, okay, I don't want to make excuses for myself because that's what I'm here for. But okay, you don't want to be a doctor. That's right. We all want to be something different. Okay, any other questions pertaining to the quizzes or the exams? No? Okay, I'm going to start the recording and we'll get into concrete mix designs. Let me just set up the recording here and we'll have it. Okay, just give me a minute here. Come on. How are those recordings that I've been putting up? Is the audio kind of so-so on it or not too bad? They're good? Okay, good. Okay, we're recording. And I'll switch. Okay. We've done the specific gravity of the aggregates. We've done the bulk density of the coarse aggregate. So we've gotten some data. There's a reason why we did those labs. Is because we needed them for the concrete mix designs. We didn't do the physical sieve analysis because you guys did them last year. And typically we do because we got the aggregates donated from Lafarge, and there's 2-3 big bins in Carsey, and that's where all the aggregates are. So we tested. We got a feel for the gradation. We have to know the gradations. But in your case, sorry, I don't think anyone was really asked questions, but we thought that that's strictly based on A1 and A2. And if we cover that, we So typically you would do sieve analysis physically in the lab, even though you had sieve analysis with Natalie last year. But because of time restraints, we figured, okay, I'll give you the fictitious density. And the same with the data I gave you for specific gravity and bulk density. That is data that you would normally generate yourself in the physical lab. So we've got that data, and now we've even calculated the FM. And then we looked at the individual gradations. And we know now that when you batch concrete, it's a mixture. Okay, the coarse aggregate goes in, you weigh it out on the scale, you drop it into the mixer, you do the same with the sand, you do the same with the cement, add mixtures, water, and so forth. Then you batch concrete. So this aggregate now becomes blended. It's a mixture of coarse and fine. And the gradation of the blended material is very important to the physical properties of that concrete mix. If it's too sandy, okay, if there's a lot of sand in it, it might be good for finishing, maybe a floor slab, interior floor slab, but it's going to require more water to make it workable. If it requires more water, it requires more cement, to keep your ratio between water and cement. And that's one thing we're going to be looking at here shortly. So aggregates are key. They take up a big volume portion of your total mix, okay? So we're going to look at the blends, and you're experimenting that right now with your labs, whether you're going to get a 68-32, I've noticed a few that way, 70-30s, 55-45. Now, we're going to go through and we're going to do a mix design where we're actually going to determine how much cement we need, how much fine aggregate we need, how much coarse aggregate we need, how much water we need, and we're going to batch, or we're going to design, I should say, in accordance with the mix design statement. The mix design statement is the City of Winnipeg. Okay, now we're going to call up, I'm going to share this, but before I do that, I just realized I'm going to pull up the specifications from the City of Winnipeg again. So we have it handy and we can review it, and then we'll look at it again. So if you give me a minute here, I can do that. I've got the other ones pulled up already, but I'm going to pull up this one because I know I didn't pull it up. Those of you that may have it handy, you may want to pull that up on your own also. And it's the City of Winnipeg specifications. Okay, just give me a second here. Come on, here am I. Okay, here. Okay, I'm going to flip to my big desktop monitor instead of the little computer. Okay, so let's share something here. Come on. Okay, you guys can see this. This is the City of Winnipeg specification, and we looked at it before. So again, let's just go to the mix design statement. That's called the mix design statement. It's not the mix design itself. It's what your mix has to meet. In other words, you can consider it as a specification requirement. So if we come back here, we can see type 1 concrete for pavements, okay? So we have a class of exposure. Does anybody know what class of exposure represents? What is a class of exposure? Anybody?
How exposed you are.
Yeah, exposed to what though?
Is it like sulfates or temperature or things like that?
Exactly. It's the environment. It's the environment around, say in this case, it's pavements. What is the environment that pavement is subjected to? If you're building pavements in California or in the Middle East, you probably don't have to worry about freeze-thaw cycles. If you're in an area where you have sulfates, And typically here, that would be below grade. So our pavements aren't exposed to sulfates. So sulfate exposure wouldn't be a concern. It would if you're designing caissons, foundations below grade. Are your pavements subjected to de-icing salts? Okay. Again, that's a climatic issue. Here we have freezing and thawing. So we add salt and sand to our pavements to relieve it of ice. Okay. At around 10 degrees, minus 10, minus 15 is about the maximum temperatures that salt will work. So a lot of people, you have icy bridge decks, you have icy pavements, and a lot of them are saying, well, why aren't they sanding? That's sand and salt mixed together. Because at minus 30, minus 40, minus 25, that salt doesn't do squat. Okay? What the salt does anybody know what the salt does? We know sand gives you traction, but what's the reason for using salt?
Melting the ice.
How does it do that?
Soaks up the water.
Well, it's because salty water freezes at a much lower temperature.
At a what kind of temperature? You're right, you're on the right track. The melting point, if you want to call it, or the freezing point, if you want to call it, the opposite. We know that at 0 degrees, we have freezing or thawing. Okay? So in this case, we can get thawing at, say, minus 7. So in other words, it lowers the melting temperature. Okay, so that's one of the reasons why we use salt. And that's why it only works at around minus 7 to minus 10, ideal. After that, it doesn't influence it enough. Okay? So again, our pavements are subjected to de-icing salts. So when we look now at a class C2 exposure, that must tell us there's various exposures. I'm going to pull up my CSA standard here, and I know you've got one, but you don't have to worry about it right now because it'll take you a while to pull it up unless you've, again, you got to go through internet and everything else. Okay, so table 1, this is out of CSA standard, and this is out of A23.1. Okay, remember our test procedures are A23.2. This is a 2-part spec. So these are the tables. And here we can see table 1 is for classes of exposure. Okay, and they have various types of exposure classes that concrete may be subjected to. C1, C2. Now we said the class of exposure that we're designing for, the city of Winnipeg says a C2. Well, here it is, a C2. It's non-structurally reinforced, plain concrete, which is our pavements. It's not structural. They're not reinforced. We only have dowel assemblies for load transfer across the transverse control joints. But in between those control joints, there's no reinforcing. So our pavements are plain, non-reinforced pavements. They are exposed to chlorides. Okay, we use de-icing salts. And freezing and thawing. We go through numerous cycles. Examples: garage floors, porches, steps, pavements, sidewalks, curbs, and gutters. And garage floors, put it this way, if you have a heated garage and you play around with that heat, you may not always heat it, you may put it on when you're working in it, and it's that much warmer in the garage. How many times you go in and you see the snow melted off your vehicle and it's puddling underneath your vehicle? If the temperature drops in your garage and starts to freeze, you're going to get freezing and thawing. And sometimes, and you may even experience that in your garage now, right where the wheel pattern, you've got delamination occurring, you've got spalling occurring on your concrete. Okay, that's attack, de-icing salt attack. Freezing and thawing, it's the cycling. So we're going to design for C2. Okay, now this is table 1, and you can see there's various. They talk about architectural, A2s, A3, A4. They talk about S1. These are the ones that are exposed to sulfates. So if you were designing deep foundations for a building, you would have to say, okay, what type of exposure do I have? Well, in Winnipeg, we have severe, very severe. So we would actually be S3. Seawater exposure, you could have sulfates. Okay, where's S2 actually? Severe. S3 is more the seawater if you're up on the coast. Okay, but we have severe exposure to sulfates in our Winnipeg clay soils. They're soluble in water. But we're on pavements, we're above grade, so we don't worry about the S classification. So we're a C2. Now, we're going to move on to another table here. These are some requirements. When we're designing a concrete mix, we need the ingredients. Okay, we need water, we need cement, we need coarse aggregate, and we need fine aggregates. And when we get into our lab, we're actually going to go through an example of a mix design. But keep these in mind. These are the four main ingredients. We know that a lot of times we may add a supplementary cementing material. Salt is conspiracy theory put in place by car dealerships in Winnipeg in order to keep customers buying new vehicles, never-ending revolving door of consumers. You might have a point there. Okay, you may have a point there. So those are the four main ingredients. And yet we use the term supplementary cementing material, and it's sometimes referred to as SCMs. And we're going to look at that shortly here. Can anybody tell me, or does anybody know what an SCM means? What is a supplementary cementing material? Anybody? Those of you that have worked in concrete, have tested concrete? SCM, supplementary cementing, fly ash is one, yes. Fly ash is the most common supplementary cementing material, and it is used in the city of Winnipeg pavements, albeit only between May and October or the end of September, but nonetheless, it's a fly ash. It's a supplementary material that has cementing properties. Does anybody know where fly ash comes from? Anybody?
Coal.
It's about coal. It's a byproduct of the coal burning industry. We don't use coal here because all our electric power here is hydro. But those plants or those cities or those countries that still use coal fire hydro generating plants, they burn coal. And as the exhaust goes up to the smokestack, it goes up with the smoke. They can precipitate it. They can catch it. So when they catch the particulates from the exhaust of coal burning, they're little spheres, and they're about 10 times smaller than a particle of cement. And they're actually round, glass-like spheres. Cement grains are flat, plate-like, okay, very thin in relationship to its width and breadth. Fly ash particles, if you look under a microscope, and we'll look at it a little later, they're round spheres. So they do have also pozzolanic reaction, the same way as cement. How many of you have taken the ACI concrete testing certification course through the college? Anybody? Okay.
Tell us more. What is it?
Anybody now involved in concrete testing, if you don't belong to a CSA certified laboratory, you're requested to be certified by the American Concrete Institute, Manitoba chapter. And we base our certification on the CSA standard, not on the ACI standard as we do in the States. But when we offer that course, and we'll be offering that again in May, again, we got to look at it a little differently this year because of numbers and COVID and everything else. In our CARC lab, we don't use concrete because we do it over a 2-week period. We're not going to keep ordering concrete every day or batching fresh concrete every day. So what we actually do is we make up 100% fly ash mix in CARC. And fly ash by itself will set up a little bit, but you can break it up with a shovel and add a little bit of water and you can rework it. It needs cement to kick it over. It's got to work together because it's got pozzolanic hydraulic reactions with the cement. So we use 100% fly ash. It looks like concrete, except it's kind of a brown color instead of gray because fly ashes are usually brown. And we can keep that fly ash mix alive for 2 weeks because we do lab demonstrations. The students come in after a theory, they have a lab practice, lab practice, lab practice, and then they do their actual practical examination. So fly ash will have pozzolanic reaction with the cement, but not by itself. But it looks like concrete when it's wet. And when it sets up, it just kind of crusts over. Take a shovel or a spade and some water, remix it, and away you go. So fly ash, okay? We import a lot of ours from Saskatchewan. We used to. Sand, the sand out of Saskatchewan, sand deposits, or Saskatchewan still has some thermal burning plants, I believe, for power. Anyhow, that's fly ash. And there's also silica fume. And there's slag cements that are manufactured from the slags from the mining industries. So under SEMs, there's numerous types of cements. Now you can buy cement from Lafarge or from Wholesome or from St. Mary's, St. Lawrence, Hudson from the States. They're pre-blended right in the kiln with supplementary cementing materials. Here for the city of Winnipeg, they're not allowed to do it. They got to batch it separately. So much cement, so much fly ash. No different than weighing out the aggregates. They don't want the blended because they feel they have more control here. Plus, we have a maximum criteria of 15%. Some plants may be blending their cements with 20, 25% supplementary cementing materials. So from a batching point of view, you have more control. You can adjust the quantities of fly ash versus cement, for example. Okay. So now we want to look at some key factors. We're going to look at the stone aggregates. We're going to look at the fine aggregate. Key now is water and cement. So you've heard the term water cement ratio or water cementitious material ratio. Before we started using supplementary cementing materials, it was just a ratio of how much water you use to how much cement. Now it's how much water you use to how much cementing materials or cementitious materials, which includes the supplementary. So when you see water cement ratio, or you see water / CM, it means the same thing. It's the water to the cementitious content. Whether that cementitious content is 100% Portland cement, or whether it's a mixture of cement, fly ash, or cement, silica fume, whatever. And the definite ratio between the two has a direct bearing on strength. So for a C2 exposure, the city of Winnipeg specified a minimum 32 MPa, okay? That's a minimum. So we're not designing for 32 MPa. We're going to design for maximum water cement ratio of 0.45. And when we actually get into the mixed designs, you're going to find out that 0.45 will give you way stronger than 32 MPa. And when I mean way, I'm talking only like maybe 40 MPa, but it's more than 32. So what governs here is the water cement ratio because the class of exposure governs it. We're subjected to freezing and thawing and de-icing salts. Okay? So we're going to design our mix with a 0.45 water cement ratio. And the reason why the city specified 0.45 is because they already know from past experience, C2, if you look at my cursor here, okay, 0.45. And then they're saying the minimum strength here is 32 MPa at 28 days. Does anybody know what this 28-day means? What's this at 28 days? Anybody? What's this 32 MPa at 28 days? Anybody know what that means? Curing time. Yes, curing should be involved. Right, Fabian. But curing definitely is going to help you reach that strength at 28 days. It's the time for concrete to reach its maximum strength. So in other words, when we design concrete, and we're going to look at some patterns, there's a relationship between days and strength gain. So when we design a concrete, we have to have a minimum of 32 MPa at 28 days from the time that concrete was placed and started to set up and we started to cure it. Okay. Now we're talking MPa because we're metric. What was the imperial designation? Does anybody know what the imperial designation was before we went to MPa?
Is it foot per pound?
Yeah, PSI, pounds per square inch. Okay. And the Americans and a lot of the literature that we're going to look at a little later, that link that I gave you for that ICMP manual, and I'll call it up here right away. They've got metric in it, but a lot of it is imperial because it's from the States. They still work in cubic yards. We work in cubic meters. They still work in pounds per square inch. We work in megapascals. Okay. For curiosity's sake, okay, 145.04 psi is equal to 1 megapascal. Okay, you can put that in your noggin in case you may want to let your mother know about it. She might be interested, right? Okay, so we're looking at C2. We're looking at 0.45 and 32 as minimum strengths. Okay. When we get into the design, you're going to see a little bit here. I'm going to ask you one more thing here. We're going to look at this table too. It talks about air content. Is there air in concrete? What's this air content? Anybody? Why do we have air in concrete? And how much do we have? And how do we have it? And what does it look like? Yeah, water wants to travel some distance, but so how does the air influence that, Vivian? Air is everywhere from Kelly, right? There's entrapped air in a concrete, and there's actually air that we introduce when we're talking about air entrained concrete. Okay, so there's non-air entrained and there's air entrained. And in our climate, in the C2 exposure, and just the fact that we're maybe not maybe we might be in a C1, we may not be using de-icing salts, but we're still in a freeze thaw. So we still got to use air entrained concrete. And that is to resist the stresses of freezing water in a concrete mix that is going to deteriorate our surface. You've seen concrete spall or peel. You might have seen that on your garage floor. Okay? You've seen it on pavements, a scaling action. Those voids, and that's right, Fabian, those voids act as relief cords. They disrupt the stresses that the freezing water wants to build up within the pavement. So if you put an air bubble in it, it'll stop. Now we're going to be doing air tests, and those of you that may have done some concrete testing where you go out with a meter and you actually physically determine the percent air in a concrete mix, you may find that it meets the criteria, the percent range that is required. However, it may still not perform well. And look at that later, because it's the spaces between those minute bubbles that is important, more so than the actual percent content. So if you look at the city of Winnipeg, where a ready mix producer submits a mix design for approval, he also has to submit performance data from tests done on that mix on hardened concrete, where they physically determine the bubble spacing. And what they actually do is they'll take a cylinder, they'll slice it lengthwise, they'll polish it, they'll put it under a microscope. And years ago, you physically traveled across a length and you counted the air bubbles. Now there's computer programs that'll do that for you. The hardened air void analysis. And that bubble spacing has to meet CSA criteria. Even though you might meet 5 to 8%, let's say you got 6% air, but the spacing factors is out to lunch, that mix won't be approved. Because it's the spacing factor between bubbles that is more important in relationship also. I mean, don't get me wrong, you still need that range of 5 to 8, But just because you have it, it may not mean you got the spacing factor. And that is a function of your materials, especially your sand, your admixtures, and very particular, your air entraining admixture. Okay? Good. Fabian, did you work in the concrete industry? Hello, Fabian? You there? Sleeping? Time for coffee? For city during co-op. Okay, good. Good. So you're involved with a lot of concrete inspection, right? On capital projects. Okay. So anyway, so we look here and we say we need an air category of 1 because it's exposed to cycles of freeze thaw. So what's this 1? What does that mean? Well, let's move on to table 3. Actually, table 4, sorry. Okay. Requirements for air content. Now, I'm going through this for the simple reason I want to give you a little bit of background before we actually get into some of the design aspects. And it'll come into play. Air content. We want to have that range. And you heard me say 5 to 8. Why? Because I know that just from past experience. And if you look at the air content category here, you can see that the air content requirements or the ranges of air vary depending on the maximum nominal size of coarse aggregate. Okay? It's the nominal maximum, it's not the maximum. So our nominal that we're working with is 20 millimeters. Okay? So if we go to air content category 1, because that's what it's a class of exposure C2 states, and our aggregates are in this range, okay? We're up to 20 millimeters. So if your concrete is going to have 14 millimeter maximum nominal size or 20 millimeter maximum nominal size, you need 5 to 8% air. And this is 5 to 8% of the cubic meter of concrete. Okay. So if you got a cubic meter of concrete and you got an 8% air content, you have 0.08 cubic meters of air in that mix. That mix is made up of 0.08 cubic meters of air. Make sense? And that's where we're going to be going with later when we're designing based on volume. And here you can see, and remember when we look at those charts, or those graphs, when we looked at aggregates, we determined that as the maximum nominal size of aggregate increased, the water demand decreased. Well, if we look at air, we can see the same thing. As the maximum nominal size of aggregate increases, air content decreases. And here you can see 10 millimeters is almost sand. Okay, so if you had a sand mix, you need more air. You need now 6 to 9%. Okay, so we know now that the maximum aggregates have a bearing on how much air we need. So again, we're looking at aggregates and how critical it is and how it affects concrete and its performance. Okay, so we're looking at 5 to 8 for our Winnipeg pavements. Okay, so far so good. Now these tables go on and on and on. If you get a chance, you can look at them. But those are the main ones that we're interested in. Here are the types of cement. And when we start talking about Portland cement, we're going to be talking about six different cements. Okay, and they're here. And the Americans have essentially the same ones, except they have a different numbering system. They have type 1, type 2, type 3, type 4, type 5. Before we went to GU, HE, MS, HS, we went to type 10, type 20, type 30. Okay, city was type 1. Sorry, US was type 1, we were type 10. US was type 2, we were type 20. But now we've gone away for that, and we're using an acronym. General use, high early, moderate sulfate resistant, high sulfate resistance, moderate heat of hydration, low heat of hydration. And we'll talk in those data when we get into cement. Okay. So it's going to lead us up to now how we're going to start designing mixes. And there's many ways of designing a concrete mix. You can design based on previous data. if you've got a mix design that you've been using for years and you've got a lot of good data built up and it shows that it works, well, you can use that mix design because you can substantiate it, that data. If you want to use that mix design and tweak it, okay, maybe you have concrete requirements that is slightly less for strength. So you can take this mix and say, well, I know this mix works. It gives us way higher. So let's tweak it. And that's going to be a starting point. So you're going to design a mix maybe based off another mix that you know doesn't work. You can go on fresh estimation of massive concrete. What's widely used is what's called the absolute volume method. And that's what we're going to use. And the simple reason for that is this is where our specific gravity is going to come in. Our fineness modulus is going to come in. Our bulk density, of course, aggregate is going to come in. When we know the specific gravities of aggregate, what can we determine on that aggregate? If we know the specific gravities, what can we determine? What other property of that aggregate can we determine if we know its specific gravity? Anybody? Density, exactly. Exactly. And if we know density and we know volume, we can determine mass and vice versa. So what we're actually going to do is we're going to physically design a concrete mix, 1 cubic meter. Because if we design it on 1 cubic meter, we can design it for 5 cubic meters, we can design it for half a cubic meter, 100 cubic meters, whatever. If you know the proportions for 1 cubic meter, 5 cubic meters would be just 5 times each individual respective mass. So we're going to design in volume. We're going to convert it to mass. Because when we talk later on about batching concrete, it's better to batch concrete by mass than it is by volume. I mean, both are acceptable. I've batched concrete by volume when I was up in a remote First Nations, way up, actually it was in Norway House many years ago. I batched it just using a loader bucket. Once I knew the volume of that loader bucket that I calibrated, and I knew the volume of each individual ingredient, I could use that loader bucket to batch concrete. But it's ideally if you can drop it on a scale at a batch plant that's been approved and it's been certified, and the scales are accurate, and you need 1,050 kgs of coarse aggregate, you drop 1,050 kgs of aggregate on the balance or on the scale, then you drop it into the mixer. So it's a lot easier. Okay. Now, before we move on, I want to bring you guys back up here to this manual. I've uploaded to you guys in your reference, and it's a good publication. And if you go to approximately page 198, they're referring to a procedure here, obviously. Well, actually, we'll go a little bit less. The absolute volume method, okay? Page 192, and you're going to look at these procedures here. We're going to look at the ones that we're going to be using, which is taken out of the Portland Cement Association. There's so much overlap because a lot of it is based on ACI, American Concrete Institute, Design 211.1, which are the procedures that are world known. They're kind of old because a lot of people are going sort of away from it, but it is still widely accepted of batching concrete. And you're going to see that the Portland Cement Association, the American Concrete Institute, they use a lot of the same tables. Actually, the Portland Cement Association adopted it from the ACI. Okay, and you've seen that I've uploaded ACI 211.1. Have that uploaded. This is taken from the metric part. And we've also uploaded Chapter 9 out of your manual that we would have been using. Now, this is Chapter 9 from a manual few years back. The one that we would have been using had we been face to face, and the Manitoba Ready Mix Concrete Association was going to donate them. It's the same manual, but it's the 8th Canadian edition. This one here, I was able to find online. The other one you can't find online unless you buy it. But it's the same chapter. They just use different table numbers because this is chapter 9, whereas in our manual, had we been using it, it'd be chapter 12. So that's the only difference. But anyhow, we're going to come to this later. So I would suggest before we get into the actual mix design, let's take a break, say 15 minutes. It's 2:02 now, so say at 2:15. I'll just stop the recording, and I won't have to send another invite. You can just log back onto the same WebEx meeting, and then we're going to get into the lab testing. We're actually physically going to go through an example following chapter 9 here when we go through it. So we're going to be using parts of this, and you're going to find out that when we're working in chapter 9, you're going to be going back and forth page after page because it always takes you back to a certain table. So we're going to look at an example. Now, this example in the manual has some different parameters than what we've been using. When you're designing your mix, and we'll get into that, you're going to be using the data that you determined on your aggregate. In other words, you're going to be using your specific gravity. So if you're group lab 1A, specific gravities for your coarse aggregate and your fine aggregates that you've determined for lab 1A is going to be using your design. If you're in lab 2B, you'll be using 2Bs. Same with the FM and so forth. The example that you're going to have in the book here, and the example that I'm going to use on here, is going to be different than the book, but it's the same format. You go same step by step. So if they're saying they're designing for 35 MPa concrete, we're designing for 32. If they say non-Aaron trained, we're Aaron trained. Okay, so keep that in mind. So let's take a break. So say at 2:15 we'll come back here. Any questions so far? There's a fair amount to cover, and there's a fair amount to it, but I'm going to suggest you're going to have to read this not once, not twice. You might have to go through it 3 times. This is where face-to-face in the classroom works great. Fortunately, we don't have that luxury. Okay? Okay, let's take a break. I'll see you here at 2:15. Okay, we're back, I guess. We'll wait a few minutes yet, or at least a minute. How's everybody's ARP project going? Everybody just about finished? Everybody talk at once, I won't be able to hear you. No,
Learning lots.
learning lots. I guess you guys don't have a lab component for your ARPs, or do you? I don't think so, right? Not for this year.
Not.
Excuse me. I think the structural group does though, because I was in Carsey. I don't know, a couple of weeks back. I had to pick something up. I can't remember. I had to go to the college just briefly, and I stopped at Carsey to talk to Art. And I think there was a couple of structural students there. I think it was under Bauman. So they do have some type of a lab component, but it's a lot tougher to try and schedule now with this COVID and the numbers, and it's tough. It's tough. Anybody doing anything on the concrete technology part of ARP, or is it all municipal design? I guess from a materials point of view, it's kind of tough when you don't have the lab capabilities. Okay, roadway design. You're talking about roadway design, you're talking about geometrics and also the thickness? Sean?
Yeah.
Yeah. Which procedure are you following for thickness design? Is it the AASHTO, or are you sort of doing mechanistic, empirical design, or just strictly imperial design?
Following more AASHTO, but also city standards.
City standards. So the city actually has a thickness design standard?
Well, recommended guidelines. It's not necessarily exact thicknesses, but ranges you're supposed to stay within.
Okay. And are you doing arterial or regional streets or collector streets, or
Kind of collector, but very low volume at the moment.
low volume? Yeah. Okay.
Yeah.
Yeah, there's a couple of good. Well, there's so much information written on it. If you DOTs in the states, they all have their own different procedures. They originally all stemmed from the Ashton Road study way back in, I think, 1966 was the first one around there, and then it sort of developed. And a lot of them now use software programs, and they design based on experience, because Ashton Road study was very, very conservative. And throughout the years, I think they basically determine what works and what doesn't work, and they go from there. Anyway, good. Maybe I'll get the chance to read some of your ARPs. Okay, let's get back. I'll do the recording. Okay, now we're going to design a mix. And when it comes to highways, they have very little concrete pavements. They do, the major Highway 7, Highway 75, Highway 9, Highway 8, and so forth. But MI hasn't changed their design probably for 30 years, and a little bit out of date, I think. So that's why we're designing for the city of Winnipeg. And even then, the city hasn't done much change in their design concept. But when we go to asphalt design, it's the same thing. We're going to design for the city of Winnipeg asphalt pavement instead of highways. For a simple reason, highway uses a slightly different procedure for asphalt design than most Canadian agencies, or even across. They kind of stick to their own guns, their own way. So different clients sort of have a different preference. So we're designing based on city. Okay. I'm going to put up a spreadsheet which ties in to, I set it up myself as a spreadsheet. I'm just using for calculations. Typically, you just write it out on a piece of paper, summarize everything as you're going along, doing your calculations. Then you can also put it into a spreadsheet after the fact. I'm kind of doing mine right on the spreadsheet, and You can understand why, and I've got it laid out sort of step by step. And it's no different than writing it out on paper, because there's a sequence of events, step by step procedures. Okay, so I'm going to call up the, where am I here? Okay. This is the chapter that would have been taken out of our design and control of concrete mixtures. That is the name of the text. And we use what's called the Canadian edition, because there they refer to, it's published by the Canadian Association, Cement Association of Canada, which used to be the Portland Cement Association. The Portland Cement Association is no longer active in Canada. They got bought out by CAC, or they changed names to CAC. In the States, Portland Cement Association is still a major player when it comes to concrete. And they've authored the same manual as what we have here. Ours is based on the Canadian metric system. This one that you see here, chapter 9, your C is going to relate to metric, but not the Canadian metric. It's the ASTM metric and also the imperial. So in here, you're going to see a 19 millimeter concrete aggregate, not 20. Okay? You're going to see 4.75 millimeter, or like the old number 4. In our manual, we would have been talking 5 millimeter. When they refer to a 2.36, or the old number 8, we're going to be talking 2.5 in our manual. So when you're looking at this chapter 9, we're going to be using the ASTM metric, not the Canadian metric, but they're all interchangeable, okay? So whenever you see 4.75 millimeters, you know it's a 5, and vice versa, okay? So this is designing and proportioning normal concrete mixtures. And they talk about certain mix characteristics. And we know from our mix design statement that the city of Winnipeg had put out, there's certain criteria that our mix design has to meet. For example, when the city of Winnipeg asks for a mix design, they ask the contractor to provide concrete that's going to give them these properties, okay? As an owner, they have no business really asking, I want to see your mix design. Why? It's the contractor's responsibility. Now, the contractor is working with the ready mix producer, okay? So really, it's a ready mix producers. Those of you that might have worked with MI always asked to see the mix design, which is wrong. Why? It's not their mix. It could be proprietary information. As an owner, you can say, I want this mix, or your mix, to give me these properties. That's all you have to ask. Who cares how much stone, how much sand, how much cement, how much water? That's none of your business. That's the ready mix producer's business. Okay? Yet when I was involved with Centerport, and we were doing the bridges and infrastructure, and the bridge department from MI asked Lafarge, I want to see your mix design. And they said, no. None of your business. I will give you a statement saying my mix will give you those properties. My mix will give you 5 to 8% air. My mix will give you 25 plus or minus 5 millimeter slump. It will give you a minimum of 35 MPa strength or whatever. But you have no business knowing how much cement and how much sand I use. None of your business. It got to the point where I requested, I was the quality guy on site, and I asked Lafarge, I says, you got to submit it. They won't allow you to pour. They won't allow you to supply concrete unless you present that mix design. And they fought and got to the point where I said, okay, you're going to be off the job. We'll have to go to a different supplier. Only then did they submit it, because MI wanted to see it, and it was right in the specifications. The contractor shall submit a mix design depicting the amount of individual ingredients, something to that effect. I mean, that was the owner's prerogative. I mean, he can ask what he wants. If you don't like it, don't bid on the job. But anyhow, so really, the city of Winnipeg here does ask for the mixed designs because they have to be submitted, and then they send it out to a third party, usually a materials testing company, to look at the mixes and approve it. And then they got to provide data on their aggregates. They got to provide data on their actual mix performance and so forth. Selecting mix characteristics. So we know some of our mix characteristics based on the city spec, okay? And these are the ones. This is what that mix has to meet. Then they're saying if you're going to use fly ash, there's some restrictions. Okay. Class CI, which is the Class C intermediate fly ash, shall not replace Portland cement by more than 15% by mass of total cementitious. So in other words, if you've got 500 kgs of fly ash plus Portland cement, total 500, the fly ash portion cannot be more than 15% of 500. Okay? Depends how you word it. Sometimes it could be percent of cement. Sometimes it can be percent of total cementitious. In this case, they say 15%. A few years, actually more than a few years, the city would not allow any fly ash. And only recently has MI, probably within the last 5 years, maybe a little longer, have allowed fly ash. MI always had a bad taste for fly ash. Anyhow, that's a different story. So this is the mix design statement. We're going to design a mix that is going to meet that. It's going to give that. Okay? So we looked at, remember I mentioned ACI 211? This is ACI 211. This is the metric part. This ACI 211 procedure is imperial, and in the back under Appendix 1 is metric. And if you look at this procedures, later on you'll see that it's very similar to the PCA. In fact, a lot of those tables come out of here. Tables that PCA are using come out of here. Okay? Instead of following this, we're going to follow the PCA Chapter 9 one. Okay? Okay. Now, give me a minute. Okay. Give me a minute here. Share. Okay, I'm going to go to my spreadsheet here. And this is something I just set up. I haven't put up this spreadsheet anywhere for a simple reason. As you do your design, and you can do it on a piece of loose leaf, then summarize your results in a table, spreadsheet, whatever you want to call it. Okay? Typically, we would do this on the whiteboard together. Anyhow, this is an example. Okay, my data, my criteria, like my aggregate data, is going to be different than yours. But the procedure and calculations is exactly the same. You're just going to use your own data that you generated from Lab 1 and Lab 2. Okay? Now, I've rewritten the design statement. Okay? Minimum C2 exposure, 32 MPa. Minimum cement content, 340. You're trying to go away from specifying minimum cement contents. Throughout history of performance, we found out that there are certain structures that should have a minimum cement content. Okay, the city here is specifying a minimum of 340. They're saying that your mix design, regardless of what it's going to be, has to have a minimum of 340. Even though you feel your mix design, let's say you can come up with a mix that with 320 kgs, you'll get the strength they're looking for. You're going to get the physical properties they're looking for. Now, no good. Got to be minimum 340. You bid the job. That's the statement. They want that. Okay? So I know there's been a lot of controversy in the industry, in the states, and here in Canada, as do the spec writers. Why? Anyhow, remember, contractors are outright responsible for the performance of that pavement. Usually joint responsibility between the mix designer, which is the ready-mix producer, and the contractor, because your concrete mix can be really, really good. The contractor may butcher it. He may kill it. He may add water all the time. He may overwork it. He may not place it properly. That's a construction. It's not the concrete's fault. It's the contractor's fault. Okay. So we're looking at the maximum water cement ratio, 0.45. Typically, you don't have to specify that. City didn't even have to specify that one because they specify C2. You specify C2, you automatically specify category 1 for air. You automatically specify water cement ratio. What the city did, no big deal. Slump. Okay, we're doing hand placement. The reason for that is because physically, had you been batching in Carsey, I didn't want you guys to have a fight with a slump of about 25 millimeter and be pretty stiff to try and make cylinders, to try and make your flexural beams. And for hand placement, that's where the contractor is going to put up the forms and he's going to pour concrete in between the forms. If you're using a slip form paver on the larger projects, highways, for example, even, you're going to go slip form paver. You want a stiff slump. You want a slump of about 25 because the pavement is being extruded out the back of the paver. If the slump is too wet, it's going to slump. You know, your nice straight vertical edges of your pavement, as it gets extruded from the slip form paver, start to slump. You don't want that. Okay. So in fact, on a slip form paving job, you'll find contractors will a lot of times reject concrete that's too wet because they can't work with it. Okay. Too wet. It's just as bad as too dry. You want to be able to work with it, it's got to perform. Aggregate size we know is 20 millimeter. That's the maximum size of aggregate. And our air content, we've known that with C2, freezing and thawing and using the icing chemicals, we have to have an air content between 5 to 8%. Now we're going to design on the higher end of this range, and I'll tell you why a little later, but most people will say, well, I'm going to design right down the middle, okay, 6.5. You can, nothing wrong with that. But my past experience has shown that every time concrete comes to the job site, if you're batching at the plant for 6.5, chances are you're going to be close to the bottom end on the job site. If I design my mix on the high end and I lose 0.5% to 1% on the job site, I'm right down the middle where I should be. Okay. Too much air is not a problem, only when it gets to the point where it's going to start taking away from your compressive strength. Okay. A high increase in air compared to design will definitely influence your strength. So you want to be careful, you know, especially when your mixes, say, are running fairly close to borderline requirements. Air can influence your compressive strength. Later on, we'll look at that. So anyways, I've kind of set up what I'm going to need. I've looked at my cement specific gravities. We know the specific gravity of the aggregates. In my example, I'm using a specific gravity of my coarse aggregate. That's 2.65. Okay, we're going to be using the oven dry, because we're designing on dry basis. What that means is we're assuming that our aggregates are bone dry, no moisture in them. Okay, you took them right out of the oven and they cooled off, and you made sure they didn't absorb anything from the ambient. So we're basing it on dry. You can base it on SSD. Okay, and when you're actually batching concrete, you have to consider what's the state of moisture that my aggregates are in. Are you taking the aggregates out of a stockpile and it rained for a week and you're now bringing it into the plant and you're loading it up in the bins over the scales and that water is just dripping down? That's water that's sitting on the aggregate that becomes part of your mixing water. You got to account for it. You just can't add water and not consider that because now you got way too much water. Okay, and we'll get into that. So I'm going to use my bulk specific gravity dry, 2.65. And for my fine aggregate, I'm going to use 2.67. And these are just examples I pulled out. Absorption, I'm saying on the coarse aggregate is 2.1. The absorption on the fine aggregate, I'm saying, is 1.4. The FM is 2.7. Okay, so I've listed the variables that I'm working with. FM of 2.7. This is why we needed to calculate FM, because we need it for our design, and you'll see where. We looked at some of our ingredients. We know we have water. And you'll see I've got something here called water adjusted. And you'll understand why shortly. Is we got to allow for that drip in water to come down if we have it. And if we don't have it, it's going to be a problem also. And I'll tell you why. We're looking at general use cement. Okay, GU, general use. It's normal Portland. It's not sulfate resistant. It's not high early. It's not low heat of hydration. It's not moderate heat of hydration. Fly ash. Let's throw some fly ash into the mix. We're allowed to do it. We can replace some of the cement. Why not? Cement's the most costly aspect. Plus, there's some good physical properties that develop because you have a fly ash mix. We obviously know we need coarse aggregate. We're going to need air entrainment, even though when we're batching it, we're going to be measuring it out in milliliters. And you pour it in with your mixing water, and then it goes in. But nonetheless, you got to add a certain amount of liquid admixture. Admixtures, when we get into it, they can be powder form. They can also be liquid form. Most of them are liquid form. And then we need fine aggregates. Okay, so now we basically got our ingredients. I'm not using any water reducers in my mix. And when we talk about admixtures, you'll understand why most ready-mix producers use water reducers. It's exactly what it says. It can reduce the amount of water. The water reducing admixture will reduce the water content. If you reduce the water to maintain your water cement ratio, you can reduce the amount of cement. Or you keep the cement where it is, you reduce the water demand because the liquid admixture is going to give you your slump, your flow. Now you've increased the strength because you've reduced your water cement mixture ratio. You kept the cement where it was, but you dropped the water. So now instead of having a 0.45 water cement ratio, maybe you've got 0.40, depending again on your water reducer. And you've heard the term superplasticizers. Maybe you're using a high range water reducer. And we'll get into that when we get into admixtures. But here, for the time being, for this mix design, we're not using a water reducer. We're just going to use air entrainment, okay? And we're going to use fly ash, which is a supplementary cementing material. Okay? Sorry, I didn't put my chat up here. I was in the chats. Anybody got any questions so far? No? Okay. We'll come back up to here. So we've got our aggregate specific gravities. Now we've got our cement and fly ash. Because we're designing by volume, we want to be able to determine the density, the mass, the volume of also the cement. Typically, Portland cements, most run have a specific gravity of 3.15. You can determine that by test. You know, if you've got if your lab is set up to do specific gravity of cements, usually these are part of the mill reports, cement manufacturer, whether it be Wholesome, whether it be Lafarge, whether it be Inland, St. Mary, St. Lawrence, any other cement manufacturer, they'll usually come up and determine their specific gravity. And fly ash usually runs in a range from about 1.9 to 2.8. So I took an average 2.4, 2.35, just right down the middle. There will be a written step-by-step procedure when we go through the chapter 9. Okay, I'm just giving you some background right now. Okay, so we'll start. Okay, if we go to our book here, if you want to call it that. Where am I here now? Come on. I'm going to see if I can keep this all on one screen here right away. Okay. We're going to go through this chapter here, and some of these tables we're going to be making reference to, okay? Air content, slump, severe exposure. You can read this on your own. It just gives you some background information about the exposure conditions, air content. And a lot of times we have tables and graphs set up. You can pull a lot of the data off the graph, but if you've got the table, then it's just a matter of extrapolating. So we're going to go to the page. It's just coming up here to the example here on page proportioning. Here it is. Examples of mixture proportioning. Okay. Now keep in mind, this is an example. The data here is different than our data, but we want to go step-by-step procedure. Okay. Concrete is required for a pavement that will be exposed to moisture in a severe freeze-thaw environment. Now I'm going to read this, trying to input our data as I'm reading it, okay? Keep attention to that. A specified compressive strength, F prime C, of 32 MPa is required at 28 days. Air entrainment is required. Slump should be 70 plus or minus 20 millimeters, okay? 50 to 90, I believe, was the range. A nominal maximum size of aggregate of 20 millimeters is required. No statistical data on previous mixes are available. So you're working right from scratch. You've got nothing to base this on. And you're going to find that as we go, we're going to have to cover our butts and go pretty conservative. Because right now, we're going to submit a mix design. So he's going to say, well, how do you know it's going to work? Prove it. I've got no data. Okay. So we're going to use some statistical deviations from tables to increase our strength criteria. And you'll see that as we go. Okay. So it's type GU cement. They're saying relative density or specific gravity of 3.0. We're saying 3.15. Okay. It's well graded, 20 millimeter nominal maximum size gravel, rounded. Relative density, I think I said 2.65. Okay, absorption of, I can't remember what ours is, but okay. So you go through it. Fine aggregate, natural sand, specific gravity 2.67, I believe, 2.68. Absorption, I believe, was 1.4. We had the finest modulus. We'll go back to ours here right away. Okay, so they've given us what we have to design for. Okay. Air and training admixture. You'll find out when we study admixtures that most admixtures are governed by an ASTM standard. Okay, there's standards for air and training admixtures, retarders, accelerators. Okay, corrosion inhibiting admixtures, water reducers, high range water reducers, and so forth. So there's an ASTM standard that has to be. The strength criteria. The design strength of 32 MPa is greater than the 31 MPa required in table 9.1. Okay, we'll go to table 9.1 right away. Keep in mind we're designing for 32 MPa. Since no statistical data is available, the required compressive strength for proportioning in table 9.11 is equal to F prime C plus 8.5. So here we're going to design for 32 plus 8.5. Okay, so if we go to the table as they're referring to, table 9.11. Come on. Okay, here it is. Okay. Because we're going right from scratch. Required average compressive strength when data are not available to establish a standard deviation. So we're designing from 21 to 35 MPa because we're 32, right? So in other words, we have to design for F prime C plus 8.5. So that's 32 plus 8.5 is 40.5. Okay. I'm hoping you can see my, where am I here? Can you see the Excel spreadsheet? Okay. Okay. I've got various criteria that I'm looking at. If we look at that table 911, remember, we're 32 MPa plus 8.5. So if we go to PCA chapter 9, table 911, okay, and we say that we're going to proportion by mass, volume and mass back and forth, and you'll see why. It's 32 MPa plus 8.5 gives us 40 and a half MPa. Okay. There's also chapter 9, table 9.3. Okay. And it tells us that our water cement ratio for 32 MPa should be 0.43. And even though here they're saying 0.45. And CSA table 1, we've got our CSA standard. So what I'm doing is I'm bringing up all the criteria. We know that CSA table, just like it says here, for class C2 exposure, water cement ratio of 0.45. So essentially, I've got some criteria now that I have to determine which one's going to govern. Okay? So going in order is one thing, but if I'm going to figure out how much cement I need, it's good to know how much water I'm going to need. Okay? So let me go back to sharing my my manual here, where they're referring to. Come on, you're not coming up here. Okay. So let's determine how much water we need. If we know how much water we need, then we can figure out how much cement we know, because we have the 3 water cement ratios. Oh, come on. This is the trouble with this manual. I guess the thing to do is always print out here. Okay. We're looking at water here, approximate mixing water. 9.5 metric inch pounds. Remember, this is American. We're strictly here. And we've got a chart here for air trained concrete down here and non-air trained. We're designing air trained, okay? What's our slump criteria? You'll get your 184 right away, Fabian. Okay? We're in air trained concrete. What's our slump criteria? What are we designing for as far as slump? 70 to 90? Right? Right. Okay. So air trained concrete, 75 to 100, 25 to 50, 150 to 175. That's your slump in millimeters. So we're going to be in this range here. Okay? 75 to 100. We're designing for it. Slump's going to vary. Slump's going to have a bearing based on aggregate proportions anyway. So it's not exact, but we know that we're closer in this range. What's our maximum size of aggregate? Okay, we're 19 millimeters. So if we come down here, you can see it's 184. Now, how did they come up with these waters? Well, if you look at the footnotes, the quantities of mixing water are for use in computing cementitious material contents for trial batches. And eventually you would do a trial batch after you designed this to prove your mix. They are maximum amounts of water for reasonably well-shaped, angular, coarse aggregate. And we are using coarse aggregate, crushed, right? Angular. So we don't have to make any adjustments. Because depending on if the aggregates are rounded or sub-rounded, you can play around with that water demand. We know we're going to need a higher amount of water now because they're crushed aggregates. Remember, crushed aggregates aren't ideal for workability because you need more water. If you need more water, you'll need more cement. Okay, so now we're looking at 184. Okay. Come on. Okay, this is where someone had asked, oh, this is the 184. So if we look at our water criteria, okay, PCA Chapter 9, Table 9.5, we just looked at that. And we determined that we needed, come on, that's probably 184 kgs. Okay, if we know the water, and we know our water cement ratio, it's easy now to calculate the amount of cement. CSA Table 1 that we looked on earlier in the earlier class, if you remember, it's a 0.45 water cement ratio. The city of Winnipeg says 0.45. So if we go through those calculations, we can determine that we need 409 kgs of cement. The Table 9.3, if you go to Table 9.3 in the Portland Cement Association, and we'll look at that right away here, it tells you that your water cement ratio for 32 MPa should be 0.43, actually less. So let's determine the amount of cement we need that using 0.43. And it's 428. But also, because this is a new mix, we got no performance data, there's no statistical analysis that tells us that mix is going to work. We want to have some nice warm fuzzy feelings in our mix. So we're going to bump it up another 8.5 MPa. And using the table 911, we now say, come on. Oh, there's nothing under there. Okay. So we'll go to that table right away, and you're going to see we're going to use a 0.34 water cement ratio. So that means with 0.34 water cement ratio, so I get 3 cement contents that are viable. Which one should I go with? Anybody? Which one do you think is going to govern? The 541 will. That's the one that's going to tells us that at least with a 0.34 water cement ratio, we have to have 540, and we have to have 0.34 because now we're designing for 40.5 MPa, not 32. We only need 32. And when you do this mix design, and let's say you use it in industry and you find out the first couple of years that your strengths are way too high, then you can tweak it. Now you now have some data that it works. Okay? But for the first go around, you have to convince your client that it's going to meet. So let's go back to those tables and we'll see. And you're going to see that what those tables involve, that you're going to have the criteria required. Now, how come it doesn't pop up the first time? I got to do this twice always. Come on. Okay. So we go to the tables here. It's going to take a little while here, but we'll get there. Oh, sorry. On the other way. Oh, okay. If we go to table 9.3, like I stated, okay, compressor strength at 28 days, 32 MPa is in between 30 and 35, okay? We're not non-air entrained, we're air entrained. So we're between 0.39 and 0.45. Well, if you extrapolate it, 32 is not quite halfway. It's actually 32 and a half, but it still works out to difference of 6 year, add 3.42. 0.42 water cement ratio for 32 MPa concrete. It's lower than 0.45, so it governs over the 0.45. You always use the lowest water cement ratio. If that's what you need, that's what it uses. But then again, now one step further, remember we said we got no data. So we got to add 8.5 for statistical. And now we're at 40.5. So if we come up here, 40 is 0.34. And that's where on my spreadsheet, you see I use 0.34. That's lower than 0.42, and it's lower than 0.45. That's what governs. Okay? So we're using 541 kgs. Everybody okay with that? So we now have determined water, and we now have determined cement. Now, if you go step by step, they go in chronological order, but I'm going to jump right to the air content because that's the quickest. That's the easiest to determine, okay? And even here, you can always read when they talk about air content, an example, they'll even specify to go on the high end. So let's just go to it already anyways. Air content. For a severe freeze-thaw exposure, Table 9.5 recommends a target air content of 6% for 25 mm aggregate. That's also for 20 mm, okay, because it's 14 to 25. When we looked at the CSA standard, it was 14 to 28. Again, 28 is Canadian metric, ASTM metric is 25. Therefore, design the mix for 5 to 8% air and use 8%. Okay? I don't want to go quite 8% just in case I'm over. Because remember, when you're batching concrete, those of you guys that may have tested concrete in the field, and if the air content in a mix in a truck arrives low, what can they do? Okay? You need 5 to 8. The mix design arrives at 4.8. Now what? What do you do? Anybody? You can blurt it out. But exactly what Fabian says, you can put some air mixture in it. Provided the concrete, okay, is not any older than 90 minutes from the time of batch, and you can add air content, you can add air admixture, I should say, to it, and mix it properly, and get the air, you can use it. You don't reject it. Why reject good concrete? Air is low. You got to remember that air is going to fluctuate maybe from load to load because it's governed by the slump, it's governed by the sand grading, it can be governed by temperature, governed by the admixture itself, mixing speed, mixing time. Now, unfortunately, in a central mix plant, the revolving drum mixer, the truck does not get it until it's properly batched and mixed. And then he dumps it into the revolving drum mixer, and then they drive out to the job site. If you're doing a dry batch, where you're actually adding the ingredients into the back of a truck, like a rural mixing plant, or if you set up a temporary one somewhere, every delivery truck becomes a mixer. And it's only as good as the fins and that truck itself. So there you have to allow longer mixing time because the trucks are batching it, not the plant. So you can see how air can be influenced by a lot of factors. So if the air is low on the job site, add some. Add some. No problem. You can do it. It's right in CSA. And if you've ever found a spec that says you can't, tell the spec writer he's full of it. Pardon the expression. Put some air in the mixture, right, Fabian? Okay? So I like to design for 7% air. And like I mentioned earlier, if it drops, I've got a little bit of a cushion. I'm not dropping below 5%, hopefully. If it goes up, I still have room about 1%. And put it this way, if the air is higher, with time it'll drop. Okay? So we go for air content. Okay, so let's look at our air content, and that's pretty straightforward. I mean, we know that air content is 7%. The volume is what? It's just 7%. Come on, how come it's taking so long? Okay, so if I come down here for air entrainment and go to CSA Table 4, there's also criteria here. And if we go there, come on. See, I blocked these out just so I don't have to retype them all. So now I can't get it. Oh, no wonder. There's no mass. Air doesn't weigh anything. Sorry, guys. Do I have anything there? Okay. So we designed for 7%. Okay, so this is mass, this is volume. Eventually, we're going to convert everything to volume. And then back to mass. Okay, so now we've got our 7%. Now, how much is 7%? Well, who's the manufacturer of the air admixture? Is it Grace? Is it Degussa? Is it Sika? Are you using Derivair 1400? Are you using Micro Air? So different admixture suppliers have different formulations. So a ready mix producer, if he's working with Grace products or Sika products, he'll eventually know that if he's using Micro Air, which is the Degussas, he needs so many milliliters per 100 kgs of cement. And you heard me say at City Mix, it was 10 milliliters per percent raised per 1 meter. Okay, good. So you guys determined that. Is there a formula to calculate how much to put in like a full concrete truck for 5 meters for air? It depends again on the product. Now, you'll notice that I've uploaded and learned Derivair 1400, I believe. Air training admixture. I think that's Grace's. I'm speaking from memory now. If you read the technical data sheet, they recommend 80 to 200 milliliters per 100 kgs of cement. Now that's a big range for covering your butts because they know there's too many outside influences that can affect it. Like I mentioned earlier, temperature, grading, water, sand content, other admixtures, okay? You may be using a water reducer, you may be using a retarder, you may be using an accelerator, whatever. They're all going to influence. So it's like a trial and error. Once that ready mix producer knows, and here, example for City Mix, they already knew that they could change 10%. 10 milliliters could change the air 1%. Just trying to read some of these comments here. Okay. So again, yeah, City Mix. So with 7% air, we'll have a little bit of a cushion. Now, you'll figure out how much you need per meter in milliliters. It could be something like 60 milliliters. Now, the reason why I'm saying, you heard me use the term per 100 kgs of cement. Most admixtures are not based on a cubic meter of mix. It's basically based on the cement content. Eventually, you can figure out that with a cubic meter of concrete, this mix design, this is how many milliliters we need per meter. So we've got 541 kgs of cementitious, of cement. So let's say we're using 80 to 200. So let's say we're using 80. Let's say we're using 80 milliliters per 100 kgs. So it's 80 times 5.41 because it's for every 100 kgs. Okay. In this case, when we're just doing the design, we're just looking for volume. Well, then it'll work out when we're actually doing the trial batch, when you're physically mixing your concrete. Then you're going to have to play around with that 60 milliliters or 65 milliliters or 80 millimeters or whatever. But they're always based on 100 weights or 100 mass. So in other words, if this was imperial, it'd be for every 100 pounds of cement. Here, it's for every 100 kgs of cement. Okay? So we would take milliliters times cement divided by 100, because it's for every 100 kg, so we get 5.41. But here, as far as determining the actual percent of the overall mix, it's 7%. And 7% is actually 0.07 cubic meters. Okay, so now we've got our water, we've got our air. Fly ash will do last. I'll let you know why, because maybe you don't want a fly ash in your mix. Maybe you're going to be placing this before April or after September. Then the city doesn't allow you to use fly ash. So when you're doing mix designs for the city of Winnipeg, you have to have 2 mixes, 3 mixes, essentially. Okay. So now, coarse aggregate. We know the specific gravities of coarse aggregate, but how much do we actually use? Okay. We're going to go back to our manual here. Come on. Why is it always double click for everything here? Come on. Okay. Cement content we've gone through. Coarse aggregate content. Okay. The quantity of 20 millimeter nominal maximum size coarse aggregate can be estimated from figure 9.3 or table 9.4. And we'll go to that right away. The bulk volume of coarse aggregate recommended when using sand with the finest modulus of, my example, I think is 2.7, is, it says 0.67. Mine will be a little bit different. We'll see why. We know our bulk density of the aggregate. I think ours is 1638, my example. The oven dry mass of coarse aggregate for a cubic meter of concrete then is the bulk density times the volume gives you the mass here. And how does that work? Well, let's go to table 9.3 or table 9.4. Come on. You can see some of these things are this graph here is the same as this table. It's just graph, okay? So remember, we look at the bulk volume. So we said our specific gravity was 2.7, I believe, right? So we're in between here. Our aggregate, nominal maximum aggregate size is 19. We're at 2.7, so we're going to extrapolate. We're exactly halfway. So we're 0.63, right? So this is the bulk volume of dry rotted coarse aggregate per unit volume of concrete for different fineness moduli of fine aggregate. And if you remember what fineness modulus is, it's an index of how fine or how coarse your sand is. So if you've got a really, really fine aggregate, you're going to have a different amount of coarse aggregate that you're going to need, because it's going to give you that combined grading. Is it going to be too harsh? Are you going to have a nice fatty mix with lots of paste, great for interior floor slabs? Okay, so you can see now how the fineness modulus of sand controls the amount of coarse aggregate you need. And that 2.3 to 3.1 range from CSA tells you how fine or how coarse your sand is. So in our case, if we go to our example here, okay, coarse aggregate. Chapter 9, table 9.4. Okay, we looked at the bulk density and we looked at the fineness modulus of the fine aggregate. if we went through those calculations, we had a bulk density of 1636, okay? FM of 2.7 for the sand. And from the table, we determined it was 0.63. So we got 1,031 kgs. So you can see what's happening here now. We've got our ingredients. We've got water. We've got cement. We've got coarse. So how do we determine sand? Well, remember, let's now determine how much volume do we actually have without the sand. We're designing for 1 cubic meter, okay? So we can actually determine the mass is quite easy. Sorry, the volume. Density of water is 1,000, okay? Density is equal to mass over volume. Volume is equal to mass divided by density. So we now have our water now is 0.184 cubic meters of the whole batch. Our our cement, I should say, we have 541 kgs. Specific gravity of the cement is 3.15 times 1,000 for water, which is the density of water. We get density. We now have the volume. So cement occupies 0.172 cubic meters of that 1 meter. The coarse aggregate, okay, we use this specific gravity times the density of water to get density of the aggregate, and we now have 0.389. So you can see here now, what's our total volume without the sand? Okay, 0.815. The rest is now, we know we have 1 cubic meter we're designing for. We now know that 0.185 is going to be the amount of sand we need. Okay, we know the volume. Can we get the mass? Darn tootin'. And there you go. Because we know the specific gravity of sand is 2.67. So we now know 1 cubic meter. And you'll see that this total includes the 184 plus the 541 plus the 1031. Okay, it doesn't include these two. So approximately 2,280 kgs for that 1 cubic meter. So we've essentially completed preliminary mix design. But keep in mind, we're designing on a dry basis. That means the aggregates are bone dry. So what's going to happen when those aggregates get batched? What's going to happen with that mix? Anybody? Okay, I've added the aggregates, I've added the cement, I've added the air and training admixture, I've added the water. Is that going to be good? I'm trying to get a slump between 50 to 90. What's going to happen? Yes, Fabian. That water, that 184 is going to get absorbed by that aggregate. They're bone dry. Now, you wonder, why the heck do I have such a stiff slump? I can't work it. I used the maximum amount of water. What's going on here? You got to take the absorption into consideration. Okay? Now, how much is it going to absorb? How much water, how much of that 184 is going to get absorbed into the aggregate? And then it doesn't even work with the cement to hydrate, to give you that strength. Remember, strength development is a chemical reaction between the cement and the water called hydration. And we'll look at that when we talk about cements. Okay, and heat of hydration. When concrete starts to set up and the cement and the water are reacting into a hardening process, you wonder why your concrete feels warm. Well, it's generating heat. And that's why if you go to Kiosk or you go to Hoover Dam, and those walls are like 30 feet thick on the bottom of concrete. Can you Imagine the amount of heat buildup that you would have, and you have thermal cracking. It's a problem. It'll generate a lot of heat. Cement with water in the chemical reaction of hydration will generate heat. And that's why, if you remember the different cements, LH, low heat of hydration, MH, medium heat of hydration, there's actually cements that will develop less heat. Okay, so that's why thickness will have a big bearing on your structure. So now let's figure out how much of this 184 kg is going to be absorbed by the aggregate. Well, that's why we did absorptions. Of course, aggregate was 2.1% times 1031, 21.6 grams, kgs, I should say, sorry, of water is going to be absorbed. And the sand is going to absorb 6.9 kgs because its absorption is 1.4 times 495. That's the mass. Remember, dry basis. So in other words, 28.5 kgs. So say 29. Or I'll go 28, round down. Now, if I'm going to lose 28 kgs, I better batch an additional 28 kgs because I know it's not going to affect my water cement ratio because it's being absorbed by the aggregate. It's filling the pores. So I'm going to give them back that amount. It doesn't affect my water cement ratio, okay? But I would add that now to my mass here. So it'll almost be 2,300 because it still adds weight, okay? I'm not so much worried about this mass here, this cubic meter here. So now I've allowed an additional, so now when I'd be writing out my water, my mix design was actually going to, on a dry basis, is actually going to have 213 kgs of water. Of that, 29 gets sucked into the aggregates. Now, what's going to happen, guys? Let's say I have that rainstorm. It rained for a week. And remember, that water just came dripping down out of the bins. Let's say my water content was 4% for the course. And say the sand was, I don't know, say 5%. Now what? Am I still going to put less? Yeah, how much less? In fact, are you going to put in less? Do we have to take away? If my moisture content here, water content is 5%. Of that 5%, 1.4% gets absorbed. So that means I'm going to have 3.6% excess water, right? And here I'm going to have 1.9% excess water. So now I have to determine how much excess water I'm going to have. And I'm going to go through that calculation, and then you have to subtract it. You'll have to subtract it from the 184. Because this excess water, the free water that is sitting on those aggregates, some of it got absorbed, 1.4% and 2.1% got absorbed. The rest is sitting on the aggregates. It calls for a maximum of 184. Now you've got excess. You have to figure out how much excess you have and subtract it from 184. We said our aggregates are bone dry. Okay? So that means we don't have any excess. In fact, we're going to lose water. So we're going to give it back to them. We're going to allow for it. Okay? So keep in mind when you're doing mix designs, and I do give a problem sometimes. I never ask you to do a full mix design on a quiz or an exam because it's going to take too long. But I may ask you how much additional water or what is the net water? And I will give you water contents. I'll give you absorption values. I may say the water contents are 0, or I may tell you what they are. So you have to determine the net water demand. It's still getting 184. but some of that is being contributed by the excess water sitting. That's why it's important when you're doing plant control. And I don't know, some of you may have done plant control where if the city, say, is paving a street 800 cubic meters, they're going to go all day. They're doing, say, a kilometer of roadway or even MI. And a lot of times the ready-mix producers are getting shipments of aggregates continuously throughout the day because they're using so much of it. So their aggregate supplier is bringing it into the plant. And again, their aggregates may have been somewhat dry, and all of a sudden they're bringing in wet stuff. And then the batcher wonders, why in the heck is my mix changing? The first 5, 6, 7 trucks on the job site were good, and all of a sudden now it's too wet. The slump is way off. The inspector wants to reject it because maybe the aggregate moisture content has changed. Now, a lot of these plants have sensors in their bins, especially for the sand where there's a lot of water. And it'll give them constant readout. But the best thing to do is just take moisture contents of that aggregate. You go up to the top of the plant, sample the aggregates out of the bin or out of the stockpiles. If he's feeding it quite extensively, take moisture contents and say, hey, to the batcher, hey, the amount of water now changed. The water content went from 1% to 6%. Okay, you're always getting shipments. So quality control at a batch plant is very, very important. You got to know what you're doing. Okay, so this batcher, a lot of it is computerized. If he knows these moisture content, he just keys that in. He dials it in on his computer, and it compensates for it. And then the computer tells how much coarse aggregate's got to be batched for this 7 cubic meter load, or 5.5 cubic meter load, depending on the size of the truck. What we used to do, and unfortunately in our pavement mix design, we take a tour of Lafarge. We do the precast plant because you guys, I think, wastewater sewer or whatever you design, see how wastewater pipes and sanitary pipes or precast pipes are manufactured at Lafarge Precast, and then half the group goes over to the plant, and we look at the ready-mix plant, witness a plant operation, and then they switch. Unfortunately, with COVID, we don't have that luxury now, but myself and Michael Robb, we used to always try and take you guys out for about a half a day tour of Lafarge. So this is the basics of a mix design. I would suggest you go through that manual and read it again. I put this up. If you want, I can put this up as an example. So this week we'll need to read the unit 3, 4, 5, 6 notes plus chapter 9 is what the extended theory behind the slab. Not so much units 3, 4, 5, 6. Talks about cement in detail. It's going to talk about admixtures. It doesn't hurt. You know what an admixture is. But for this lab, the main function is knowing how to design the mix. When we look into units 3, 4, and 5, we'll see how cement is. Look at the 6 types of cement. We'll look at how cement is made. I've put up some YouTube videos. I've got some YouTube videos that shows actually how cement is, what clinker is. Why do we add gypsum to cement? What are the 6 types of cement and when are they used? We'll look at admixtures, just the main ones, because there's numerous admixtures, but we'll look for the air training. We'll look at the retarding admixtures. We'll look at an accelerating admixture and what they do. What are the performances? Okay. We'll look at the high range water reducers. Now, fly ash, good point there, Fabian. We can add fly ash to the mix. City of Winnipeg allows you 15% maximum of total cementitious. That means 15% of 541. Okay? If it's total 541, then this is going to reduce. Okay? Because this is 541 total. Of that, 15% of 541 is, oh, I didn't figure it out. 10% is 54, 27, 81. Okay? So now this has to reduce by 81 kgs, right? So what does that give me? 460? Okay. Now, because the specific gravities change, it's not going to change much because the specific gravities are different. this volume now is going to change. And you're going to come up with a volume here using a specific gravity of 2.35. I always use fly ash last because when we were actually doing the practical mix designs, some groups did a fly ash mix. Some said, well, I only want to use 8%. I left it up to the groups because when they were batching concrete, we were batching in 2 separate days, 2 separate groups per day. So now group 1A became part of group 1ABC, a group of 9. Because if we had to batch concrete per group, you'd be there forever. So we said, okay, groups 1A, 1B, 1C becomes 1ABC. Group 1D, 1E, 1F becomes 1DEF. So each have an hour now to batch concrete and test it. And then the next 18 students, because remember, we're always working with labs of about 18. But because now we're just doing paper batching, each group, 1A has their own mix design. Now, keep in mind, one thing yet. Somebody, I want you to pull out your calculator, okay, and give me the percent sand as a percent of total aggregate. Okay, in this example, I've got 494. I got a total here of what? 1535. So what's my percent sand of total aggregate? I don't have my calculator handy, and I usually do these things in my head, but right now, forget it. And what's 494 divided by 1535? Anybody? $32.2, 32%. So that means my course would be how much? 68, right? Okay. Now, that's what my mix design says. And I know that a lot of your blend combinations happen to be 68, 32. But what happens if your blend combination was 70, 30? And yet your mix design is 68, 32. Now what you got to do is go back and check. If I blend my aggregate 70, 30, in other words, you're going to blend it to your mix design. If your blend, to get it in spec, let me reword that. If your blend, to get it to spec, was 70, 30, and your mix design says it should be 68, 32, is a blend of 68, 32 going to meet the grading spec? Now you got to check it. If it does, you're good. If not, we can play around with this. If I change this to 70 and 30, these quantities change individually, but my total aggregate, is still the total. It's just the proportions change. It's not going to affect 2% either way. It's not going to one way and 2% the other way. It may not change the performance of that mix much as far as workability, finishability. So in other words, your mix design should meet your grading spec and vice versa. Is that clear? Okay. In this example, it just happened to work. And I know some of you have a 6832. Now this is only my example. Your example is mix design based on your values that you've determined on your previous lab is going to change these numbers. And you may get 6931, whatever, I don't know. But always check the blend combination as per mix design. Does it meet the blend combination in your lab 2 to try and meet that envelope? You may find out that changing these mix proportions may help your blend and vice versa. I haven't looked at everybody's individual yet because a lot of them aren't handed in yet. Okay? So this is what we call tweaking. And then later on, I would never design for that. I'm going to leave you guys there. Design for 1 meter. When I would send this to the client, I would change these numbers to get about 1.02 cubic meters. Why? Why would I design for more? Fabian, you did inspection. Were you ever short of concrete? Okay, contractor, yes. Why? Wasted. But let's say you delivered 4 loads and the 4 loads were supposed to fill the box and you dumped every truck out and then you're still short. And the contractor checks his calculations again and says, no, to fill this box, okay, to fill this box, I'm supposed to have 20 cubic meters. They delivered me 20 cubic meters and I'm short. If anything, if there was reinforcing in it, they usually don't subtract the reinforcing away, and he's still short. What happened? So now the contractor's peeved off because the ready mix producer is shortchanging him. No, not so much evaporated water. We'll do later on, when we get your mix design done, you're going to calculate a yield. His numbers say he's batching or designed for what's stuck in the truck, yes. Or he's not making 1 cubic meter. Unless you check your yield, and we're going to do a yield calculation, maybe his design is 0.98 or 0.995 or 0.99, not a cubic meter. So after X number of trucks, there's less and less concrete. So he didn't deliver 20 meters. Maybe he only batched and delivered 19.5, and you're not going to get everything stuck in the fins. It's not a deliberate short change, but you don't want to peeve off a good client, so you always over-design a little bit. I don't want to design 1.5 or 1.2 because then I'm giving it away, and I'm not that rich as a ready-mix producer. So I design a little bit larger than 1.0 cubic meters to make sure, because aggregates change, moisture content change, the degree of accuracy of batching is a plus or minus variance. So you want to make sure as a good ready-mix producer and a supplier that you don't shortchange a client. But at the same time, you don't want to give concrete away because then you won't be in business very long, right? So we do a yield. So typically when I go look at this, I would bump this to 495. Just round up to the nearest 5. I might even go up to 500. Okay? And then your volumes change, and then you can see where you're at. 1031, I'll go to 1030. It's an even number. Cement, you don't want to play around with. You always want to go up because if you ended up in your yield, remember your yield, when you do a yield, if you're using 460 kgs of cement and you're yielding more than a cubic meter, then you're shortchanging and the city gets peeved off. They said, my minimum states, and your mix design states 460. You're only giving me 458. Got to take that into consideration. Cementing factor is what we're going to come up in the next lab. Cementing factor, when we analyze this mix after as far as yield and mixing. So you got to do a yield test. Am I in fact batching a cubic meter or am I batching 0.995? And that comes in from a density test. Some of you guys that may have done it, you physically do a density test in an air meter bucket. Then you know how much, that's a 7-liter pot. Okay, that's 0.007 cubic meters. It should weigh so much that when you back calculate it, you should have a minimum of a meter. You might not. If that density is less, it's telling you don't have. Okay, that's why we do a density test, is to check the mix design. I'm not doing it just to keep us busy. Okay, so I round these up sort of to the nearest 2. Remember, when you go to a plant, the scale can only read to the nearest 2 kgs or 5 kgs for aggregate, or for, I think not even that. I think for at a plant, Well, maybe now with the new digital balances, scales, but I remember one time an aggregate scale could only read to the nearest 10 kgs. So why would you go to half a kg or something like that, or 1 kg? Okay, so round up or down. So here I would go 460. I'd probably go up to 82 here. I would, or 80, as long as I don't exceed the 15%. I can be less. I can be 14.6. That's maximum. I can be 10%, or I could be nothing. It's an option. Okay, that's why it says 15% maximum of total cementitious. Okay, so it's not a direct science or art. I don't know what I want to call it. There's a science to it, but keep in mind the degree of accuracy. I remember one time they used to measure slump to the nearest 10 millimeters. Now they dropped it to the nearest 5. And I remember with MI, I saw one MI technician recording slump to the nearest millimeter. And I said, come on, give me a break. You can't read that close. All I got to do is take my tape measure and move it ever so slightly to the top of the concrete after it slumps. And I've already changed it by 3 millimeters. Come on, guys. We're not building a watch or a piano. Okay? So there's a degree of accuracy. What do these numbers really mean? And in the mixed design, yes. Okay, you got to have a starting point. Now, when I used to do concrete mixed designs for the industry, I know a lot of ready mix labs say, well, I got to do a trial batch. To me, I was wasting the ready mix producer's money. I could say, yeah, I'll batch this mix in the lab. I'll make cylinders and I'll break them and I'll say them trial mix design. But why? I'm batching with a small mortar mixer. I would say to the ready mix producer, here's the mix design. You go batch it because you're going to use the same plant batching this trial mix that you're going to use for the project. Batching at a concrete plant is totally different than using a mortar mixer to batch in the lab. You're batching 0.07, not even, maybe 0.1 of a cubic meter. Go batch 7 cubic meters because the degree of accuracy of the plant is now being used for the trial batch. You see? Then you're talking oranges and oranges, not apples and oranges. So he can still go through a trial batch, send it to a job site maybe where clients say, yeah, you can try out a mix. I don't care. I'm just filling a slab for my driveway or something, whatever the case may be. Or maybe they're going to pave their parking lot at the ready mix plant. Let them do that. They'll pave it. They'll make cylinders. They'll cure them properly. They'll send them into the lab, and the lab will test and say, yeah, nice. Our mix design works. Why try and do a trial batch in the lab, and yet everybody states you have to do a trial batch in the lab? The labs love it because more and more groshi. There's more money for them. $2,000-3,000 for a trial batch. Okay, I would say to a client, no. As much as I'd like your money, what's it really going to mean to me? And yet everybody says you got to do a trial batch in the lab. I don't buy that. Do it using the equipment you're going to use. Then you're looking at the same type of equipment, same degree of errors. That plan's got to be calibrated. It's got to be running right. No two ways about that. It's got to be functional. Okay? But your total different shearing of concrete is totally different. Mixing it in a small 6 wheelbarrow mixer versus Lafarge's big central plant that'll mix 12 cubic meters in a shot or whatever the case may be. Okay? Does it make sense, guys? If you want, I'll put up the spreadsheet blank for you if you want to use it or make up your own. Or I just did this for my calculations because I wanted to make sure you guys understood where we're going. When you're looking at chapter 9 there, you're going to have to go back and forth with those tables. That's the way that chapter is set up, unfortunately. Marcos, yeah, okay, I'll put it up. I won't put in my formulas. I'll just give you a PDF copy of it, and you guys can play around with it. Okay. But you can see here we calculate some of these things by mass, and we got to go halfway through it or 3/4 of the way through it. We convert to volume so we can determine how much sand we have. Okay, and then we need the sand. Any other questions? Again, please contact me if you're having any issues. Now, if I've covered it, then I may direct you. Keep in mind, I don't always give out answers freely, and it's not that I want to be an idiot about it. I want you guys to learn because it's way too easy to always get someone to give you the answers. You gotta learn how to find them. And you're working in a group. If you're coming to me, that tells me you can't find it in the recordings, and your other two lab partners or three partners don't know either. Or you didn't check with them. You got to check with one another. This is a team effort. You can all design your own, and that's a way of checking one another, by all means, but work together. Again, I'll say it now, a report is not needed, a letter report, but when you do this mixed design, show me your calculations like I have here. They don't have to be on a spreadsheet. They can be handwritten notes, and then just summarize it. Okay, water adjusted, GU cement, and you just put those numbers beside it. But somewhere on a handwritten note paper, it doesn't have to be typed, as long as I know your lab number, your lab group, and I can read it. I have to be able to read it. Okay. Not everybody's handwriting is legible or readable, but please, when you're making numbers, is it a 5 or is it an 8? Is it a 4 or is it a 9? Is it a 7 or is it a 1? So don't necessarily need, if you want to give me a letter report, that's fine. You're not going to get any extra marks for it. Maybe you would. We'll see. But essentially, I want is a table or a spreadsheet, your handwritten notes, as long as every page is labeled, and I can read it. That shows me what I just did here, how we went through these calculations. Okay. Tell me, like I did here, we use CSA table, we use the PCA table, we use CW3310. Give me your mix design statement. What does our mix have to meet? Because this you have to do with every mix design. When a ready mix producer submits his mix design, if he submits it, typically he'll submit a mix design statement and says this code 320PAX5T67 is the mix design for this project, which will meet the criteria specified in the following design statement. Okay? It doesn't necessarily give you this, unless you're MI and you request it, or if you're City of Winnipeg and you request it. Okay? He doesn't have to give you the mix design data. He just has to confirm that this code is this mix design meeting this criteria, okay? So in your case, though, I want to see how you got these numbers, just like I want to hear. So show me your calculations. And again, you can just do it on a piece of loose leaf and then summarize your data at the bottom. Mix design, cement, water, fly ash, coarse aggregate, fine aggregate, air training agent, by mass, the volume. So in other words, exactly what I did here. Okay? But you don't, in my calculations, it doesn't have to be on the table. It could just be in order. Is that okay? Everybody understand that? Because I've had comments about the blend combinations. You don't have to send a letter report, but use footnotes, use statements, use underneath notes, use remarks, just like some saying the blend combination failed to meet the grading limit, blah, 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 on the 10 millimeter, the 5 millimeter, and on the 2.5 millimeter by such and such percent, such and such percent, such and such percent, respectively. He gave me a graph. Also, when you guys are plotting, you do not have to put one plot per page. You're going to see that when I do asphalt, on one graph, I'll show you 4 individual aggregates plus the blend, all on one graph. So your coarse and fine aggregates, some of you guys gave me the individuals and then you did the blend, that's fine. But if you look at the grading limits for the fine aggregate and you look at it for the coarse aggregate, they're on different parts of that sheet, other than the 200s are going to meet. But they're separate. So why waste paper? Put them all in the same graph. Your legend will be on the bottom, will dictate it. Okay? You don't have to put one gradation curve per sheet. To me, that's a waste of paper, a waste of time. But, you know, plus as a client, last thing I want to do is start flipping pages, page after page after page. Put it all on one graph. I mean, there's going to come a point when there's too much on a graph and you can't read it, especially if the grading limits overlap. But okay, you look at the A-base spec for the city of Winnipeg and you look at the A-base spec for MI, they're very similar. There are some differences. So if you plot them, you'll see that their grading limits will overlap because the A-base for city of Winnipeg is somewhat different than the A-base for MI. Very, very close. Okay, so any questions so far? Clear as mud? If this was geotech? Okay, there's a lot of information here, but take it step by step. Again, if there's something you're not sure of, let me know. If your lab group can't help you, remember, you're a group of 4 or a group of 3. 4 heads are better than 3, 3 are better than 2, and 2 is better than 1. Use one another. Okay? We've gone on here for about an hour and a half now. Any questions? If not, then we can call it a day. Good? No questions? You guys are all experts in design then. Okay? So again, PCA, you can try that. I've got other methods that are very similar, but I thought PCA might be the easiest one to follow. I mean, that ACI 211.1, if you have a minute, you may just want to look at it just to compare it. But if you go through it, you'll see it's virtually the same graphs, same tables for PCA, because one dwells on the other. CSA will even use in their footnotes that they acquired it from ACI. PCA will sometimes even quote CSA, that they used it from CSA, so there's an overlap, okay? Okay, there's nothing else, then we're done. Have a good evening, a good week. Like I say, my emails are always open. Okay, thank you.